right, the last topic from 1.1 to 1.2 is continuity, which you should be familiar with a continuous function. Everything we do in this class is going to be involving a continuous function, or parts of the function where they're continuous. That's what we're going to be looking at. We only want to do stuff to functions on their pieces if they're continuous. And it's actually one of the first concepts that's its technical definition involves a limit. Alright, so the concept of continuity and limits, and really just understanding what continuity is and be able to determine when a function is continuous or not continuous. Alright, so a function's continuous if it has no holes, gaps, jumps, or breaks in it. And so usually when they introduce this in algebra, they say, if I can draw a function without lifting my pencil, it's continuous. And so an example would be any polynomial function. Right? If I take this and I draw it, well, there's my function. Right? There's no holes, gaps, or asymptotes. There's my function f of x, right? It's continuous everywhere. I could draw the entire thing without lifting my pencil. Continuous everywhere. Well, not all functions are that way. All right, so the precise definition of continuity, all right, which again we don't really even deal with in this class, but it's just important for you to at least see it, to understand that there is, we usually use in mathematics limits in our definitions because we can prove things using limits. Since this is not a proof class, you don't really have to know it, but it should be at least aware that it exists. So the precise definition, or the technical definition of continuity, is a function is continuous at a number. If the function is continuous at a number c, the following conditions have to be true. First of all, it can only be continuous on values in its domain, and this is actually the big one. All right, most things will fail this first point. If it passes the first point, all right, the value c is in the domain, it's got to pass the second point, which in the guided notes, it didn't cut and paste, so I'll have to listen here. But the second point is its limit exists at c, so the limit as x approaches c on both sides of my function exists, so I can find it. It's defined. But not only exists, it's actually a special type of limit. It's one where the limit actually equals the function value at that moment. The point on the curve is equal to the y value. If I go back up here to the picture where I've drawn my continuity, you'll see that's true. If I pick any point on this curve, so we'll say that's my x value equals c. All right, the y value would be f of c. Right, from the left and the right, well, it would be approaching that y value f of c. And so the limit would exist and equal the function value. If that's true, then it's continuous. All right, and again, we don't usually hardly ever check the second step because usually if it passes the first step, the second step checks itself. All right, but we do, again, there are some occasions where you've got holes in the function where you've removed it, and that's the case. Right, so looking at an example, right, using the definition. All right, so I've got my graph here. Right, so here's my graph of f of x. So here's my x-axis, here's my y-axis. So it's a little hard to see them, but those are my x and y-axes. And so what we're looking at first is at -5. So -5, 1, 2, 3, puts me here. There's my -5. All right. Does the limit as x approaches -5 on both sides exist? Well, on -5 it approaches that moment. That moment is the point -5, 0. The y value is 0. So yes, it approaches 0 and equals 0. So the limit exists and is equal to 0. All right, well, what's the function value at -5? Well, the function value at -5 is that moment. When I plug -5 in, I get 0 out, so the function value is 0. My pen. Switch to a different pen, see if it works. Yeah, there we go. All right, so the function value. So the limit definition holds true. The limit exists and is equal to 0. All right, is it continuous? Yes, it satisfies the definition. The limit as x approaches 5 of f of x equaled f of -5. Sorry, I put a negative. And it was 0. All right, so, and if you look at it, you'll see it is continuous. There's no whole gap or asymptote at -5. Right? It's continuous at that moment. All right, so this is just kind of giving you an idea of understanding of the continuity definition. All right, so the second example is going to be the case where it fails. So same graph, but now I'm going to look at where I've got that weird little kink in the function. All right, so at negative 2, right? This would be at negative 2. So the limit at negative 2, so from the left of negative 2 and the right of 2, well, the function puts me up here. The left of negative 2 and the right of negative 2 is approaching this point, negative 2, positive 2. And so it's approaching positive 2. The y value that it's approaching is positive 2 on the left and the right. So the limit exists and is equal to 2. Positive 2. The function value, well, what's the function value? So f of negative 2. So f of negative 2, well, it doesn't exist here at 2, right? That's an open circle. Where it exists is, well, this is what we call removable continuity, discontinuity. So we've taken this point and moved it down here, and so this is the point negative 2, 0, and that is a point on my curve. It's a closed point on my curve. And so when I plug negative 2 in, I get 0 out. And so f of negative 2 is 0. So this is the special case where it has discontinuity when the limit exists, right? The limit existed, the function existed, but those two values were different. Since they're different, they are not continuous at the moment. And you look and see there's a jump there, right? There's a gap, there's a hole in the function. I can't draw this without lifting my pen. I have to draw the first part, and then I have to come back and fill in the circle at negative 2, 0. And so it is not continuous at negative 2. And so that's trying to get you to understand that limit definition of continuity. But like I said before, as long as you understand intuitively what continuity is, that's the important part. All right. All of the things we're going to do in this class will be on, basically the definition will start if the function's continuous on an interval. All right, then we can do this. If a function's continuous on an interval, then we can do this. All right, and so a function can be continuous at an interval. If an interval just means many points, more than one. All right, from point 2 to point 5, that would be an interval. All right, and so we're going to look at an example of where it's continuous over interval. So this function's got some discontinuity. So here's an example. All right, so there's a few places where it's discontinuous, but most of it's continuous, right? This piece right here from negative infinity to negative 4, well, it would be continuous from negative infinity to negative 4. Now, there's a break at negative 4, and so it's discontinuous there. But then this piece is continuous. So it's wherever I could pick my pen up and draw it without lifting it again. All right, now wherever I lift it, that's a break. That's a discontinuity. So I can draw the first piece here from negative infinity to negative 4, continuous. Break at negative 4, discontinuous. Draw it from negative 4 to negative 1, break. Draw it again from negative 1 to 4, break. And then draw it from 4 to infinity. And so there are 4 intervals where I've got continuity. Right? There are only 4 intervals where I can say I'm continuous. There are 3 breaks in my function. All right, so that's the first question. Where is it discontinuous? And it's always at the x value. So it's at the first x value, it has discontinuity as negative 4. The next x value where it was discontinuous was at negative 1. And I forgot where the next one was, at positive 4. All right, so there are 4 places where there's a break in my function, right? Discontinuous here at the asymptote negative 4. Discontinuous here at the open point negative 1. Discontinuous here at the open point and the jump at 4. All right, then it's asking you over interval. So this would be an interval. So between negative 1 and 4, is it continuous, right? That would be an interval. So I go up to my function, and I look between negative 1 and positive 4. All right, so between negative 1, so negative 1 would be here. Actually, I'm going to switch to a highlighter. Negative 1 to positive 4. And so it didn't include negative 1 and it didn't include 4, right? That's what parentheses mean. Between negative 1 and negative 4, yeah, between those two numbers, there's no breaks. And so it's continuous. So the answer to that is yes. Yes, between, not including negative 1, but between negative 1 and 4, not including 4, it is continuous. All right, the second interval, negative 8 to 0. So I go up to my function and I look at negative 8. So negative 8 is here. And then 0 is here. Well, if I'm looking at that, well, there's actually 2 places it fails, right? It fails at negative 4 and negative 1. And so the answer to that is no. It is not continuous between negative and 1. There are 2 breaks at negative 4 and at negative 1. 2 breaks in continuity. the last thing, as it turns out, for almost all of the functions that we deal with the exception of piecewise functions, linear, quadratic, polynomial, power, root, all of our main functions are continuous. That's why I said that domain piece was really the most important part. If our function, if we can find its domain, we know where it's continuous. So for all of our typical functions, we have continuity over the domain. So it's discontinuous wherever they don't exist, wherever it breaks in their domain. Right? And this actually is a theorem. Again, we're not going to go into it. All you really need to know is if you have the domain of the function, you know where it's continuous. For these types of functions, for the linear, quadratic, polynomial, rational, root, and power. All right, so the first example is a quadratic case. All right, use the domains, and then I'm going to pop up the graph here. I'm just going to sketch the graph, but you can pop it up on your own calculator to double check my graph if you want to. All right, but the first one, this one's a polynomial, right? There's no division, there's no roots, and so there's no problem, right? Domains are, I only have to check, make sure there's no division by 0, and there's no imaginary numbers, and there aren't any. And so my domain is all reals, writing that in interval notation, which is one of the things we reviewed in the review. Negative, infinity, to positive. This function exists everywhere. There's not a single moment where does not exist. There's not a single asymptote, not a hole in the function, not a break in the function. And so it's continuous over all real numbers. So it's continuous everywhere. If you graphed this function, it's a cubic. You might have to zoom out to see it. It's actually a very simple cubic. It comes down really fast. There's like a little kink in it there, and there's an S shape. That would be the shape of the function. And so it is completely smooth, and there's no breaks, holes, or gaps in the or asymptotes in the particular function. It's continuous everywhere. It's domain, all real numbers. All right, the second example is a rational function. All right, so rational function means it's a polynomial divided by, so I've got division. And so when I find my domain, which again, this is something that you practiced in the reviews, it's all x values as long as I don't have division by 0, so such that denominator doesn't equal 0. The x squared minus x minus 6 cannot be 0, so that's what I have to figure out. Well, when is that 0? I'm going to solve it by factoring because this is a simple case. All right, x squared breaks up into x, and then I add, what are numbers that multiply to negative 6? When I add, I get negative 1. So negative 3 and positive 2. All right, negative 3 and 2 give me negative 6. Negative 3 plus 2 give me my negative 1. All right, each one of those will give me out a 0, so this will give me a 0 at 3. This will give me a 0 at negative 2. If I plug 3 in, I get division by 0. And if I plug negative 2. So those are the two numbers I can't beat. All right, I have to throw out 3 from my domain. I have to throw out negative 2. And so the domain is everything else. So there's a break at negative 2, and there's a break at positive 3. And so using interval notation, everything works from negative infinity up to my first break. Well, my first break is at negative 2. Then there's a break, so parentheses. And then I start from negative 2 to my next break. My next break is at 3. So everything between negative 2 and 3 is fine. It's continuous between negative 2 and 3. Then there's a break at 3. And then after 3, it's continuous everywhere. All right, there's not another break. And so that's its domain. That's also where it's continuous. All right, continuous over those pieces of the function. And if you graphed it, like I said, you could pop that in your calculator graph, and I'm just going to give you the sketch of it to show you what it is. But you can always plug it in your own calculator and check my graph. And so there's a break, so you'll notice there's a break at negative 2, which I'm going to write my asymptote as a dotted line, so negative 2, and there's a break at positive 3. All right, and then the graph has a piece over here, breaks, then there's a piece down here, breaks, then there's a piece over here. And so you'll see there's discontinuity at negative 2, discontinuity at 3, but everywhere else is fine. This piece is continuous. All right, between negative infinity and 2, continuous. This piece is continuous. Between negative 2 and 3, perfectly fine. It's continuous there. I can do stuff on it because it's continuous. And the same thing for the last piece. Between 3 and infinity, also continuous. And so I can do stuff there because it's continuous. All Alright, so I did a polynomial example, a rational function example, and then now I'm going to do a square root example. So this one, I can't have imaginary numbers, right? Square roots, I have to have real number value. We only do real numbers in this class. And so to find my domain, I want all numbers such that I get real numbers, which means underneath the square root has to be positive. So my x plus 10 has to be positive, and it can be 0. Square root of 0 is 0. 0 squared is 0. And so it just has to be positive. So this is what has to be true. And so you solve that. So I'm going to move 10 to the other side. So x has to be bigger than or equal to negative 10. Negative 10 is fine, right? If I plug negative 10 and I get 0. You can always check your numbers if you're unsure, especially if there's a case where you have to flip the sign if you divide by or multiply by a negative. This one I didn't have to, but again, you can always check your answer. If you plug a number bigger than, so 0 is bigger than that, you can check it out. If I plug 0 in, I'm fine, right? If I plug in 2, I'm fine. All right, so bigger than negative 10. Right, so you're using interval notation. That would be going from negative 10, greater than, which means shooting off to infinity. Negative 10, it's equal to, and so you put a bracket. That's its domain. That's also where it's continuous. If you looked at the graph of this function, drew my line, my x-axis, I'm going to draw my y-axis over here. It goes back here, it starts at negative 10, and then it's sort of, again, it's the parabolic shape. That would be the square root of x plus 10 if you graphed it. Alright, so you want to make if you are graphing this on the calculator, you might want to make your window a little bigger than the standard window, just so you see it. Right, but you'll notice it is smooth and continuous from negative 10 to infinity, right? If I take my pen and draw it from negative 10, I don't lift it up forever. Right? There's no holes, gaps, and asymptotes between negative 10 to infinity. Now, from negative 10, past negative 10 to negative infinity, it doesn't exist, so it would be discontinuous. So over here, does not exist, discontinuous. Only continuous from where it starts and then to infinity. Alright, so that finishes up for the first set of notes, the 1112, limits and continuity. Alright, so we'll stop there. You should be able to go on and do the homework over 1112, so make sure you do that. You get as many tries as you want. The idea is that you keep trying until you get it, right? Keep trying until you get it. Alright, we will stop there.